My name is Guglielmo Grimaldi, and this is the video abstract for the paper A New Characterization of the Holographic Entropy Cone by Matthew Hedrick, Veronica Hubany, and myself. In this paper, we investigate the holographic entropy cone, which is a set of entropies that subregions in holography, computed by the RT formula, can have. These are subject to inequalities like the following. We had two main objectives. First, understand the structure of the holographic entropy cone and the inequalities that determine it. And two, determine if entropies computed from the covariant HRT formula obey the same set of inequalities. The first question is important to learn as much as we can about the physics of holography. The second question is important because when working in the HRT regime, all properties of holographic entanglement become general relativity theorems, so dynamical inputs like the equations of motion, energy conditions, and boundary conditions all play crucial roles. In this paper, we make interesting progress in both of these questions. We begin by entertaining the idea that there exist counterexamples to the second statement. The best way to search for counterexamples is to start with configurations that saturate a given inequality, then perturb the geometry slightly to try to violate it. The only known configurations that saturate a given holographic inequality and are not trivially robust under perturbations are what we call light cone configurations. These are configurations where the field theory is in Minkowski space, the state is in the vacuum, and the regions lie on a common light cone as shown in these two examples, pertaining to 2- and 3-dimensional boundary. Something very interesting happens when evaluating a given inequality on such light cone configuration. Considering monogamy of mutual information as an example, entropies that do not contain a central region, the one containing the apex of the light cone, are degenerate and cancel out of the inequality. On the left, we show how the situation would look like holographically. The HRT surfaces lie on the bulk light cone, and the only non-degenerate surfaces are those computing the entropy of a subsystem containing the region A. We call this procedure a null reduction. Evaluating MMI on the light cone configuration equates to considering its null reduction over the region A, which reduces to an instance of strong subadditivity. Perturbing the bulk, we show in the paper that an inequality in a light cone configuration remains a true inequality if the following conditions hold. First, the metric perturbation must obey the null energy condition. This first condition is automatically satisfied since it is required by consistency of the HRT formula. Second, each null reduction of the inequality must obey what we call the majorization property. We derive the majorization property in details in the paper. Here we show how it works in practice. Consider MMI as an example. Begin by taking its null reduction on the region A. We then make two vectors, one for the left-hand side and one for the right-hand side, by replacing each term in the inequality with a sum of positive variables associated to each region. For example, here S of A is replaced by A, and S of ABC with A plus B plus C. Majorization is a tool in math that allows us to quantify how much more spread out a vector is in relation to another vector. If the right-hand side vector majorizes the left-hand side vector, then the majorization property holds for the inequality. By placing the numbers on the real line, this property is manifest for MMI. Therefore, MMI passes the test, and the inequality is robust in the HRT regime. This of course is no surprise, since MMI is known to be obeyed by the HRT formula. In the paper, we show that thousands known holographic inequalities obey the majorization test, without ever finding counterexamples. This led us to formulate our first main conjecture of the paper, which says that all holographic entropy inequalities pass the majorization test. While not a surprise given the enormous prior evidence, it is nonetheless a highly non-obvious mathematical result. What was a complete surprise was to discover that also the converse statement seems to hold. That is, of all possible inequalities involving linear combinations of subsystem entropies, only the holographic ones pass the majorization test. The statement is extremely remarkable for a few reasons. It provides us with a whole new characterization of the holographic entropy cone through majorization theory. It also says that any inequality that can be violated in a static state can also be violated in a light cone configuration. Furthermore, it gives us a new way of searching for new holographic inequalities that is incredibly efficient. There are many open questions that we encourage our readers to jump in, two obvious ones being finding proofs for the conjectures and understanding the physical implications of majorization for quantum gravity. Thank you.